This little video segment will talk about the design of rolled steel beams. As we already have talked about repeatedly, the AISC concept for rolled steel beams relative to bending moment is basically a concept that says my beam's design capacity must be greater than or equal to the required moment on the beam. Now, depending upon which method you're using, LRFD for instance, the design moment capacity is based on a resistance factor times the nominal moment capacity, and that has to be greater than or equal to the factored moment that's on the beam. Now again, that factored moment M sub U is going to be a product of LRFD load combinations, placing service loads into those load combinations, and then determining what the maximum moment is on your beam. For ASD, it's similar. We have a design moment capacity that still uses that nominal MN, but this time we divide it by a safety factor 1.67. That design moment capacity must be greater than or equal to, again, the required ASD moment. This ASD moment takes the service loads and plugs those into the load combinations, and then in turn develops a moment diagram or determines the maximum moment based upon those. We've talked about the modes of failure for a rolled steel beam. We've basically said that it will fall into one of three categories if the beam is a compact beam. The first category is plastic moment capacity. The second category is inelastic lateral torsional buckling. And the third category is elastic lateral torsional buckling. Each of these categories has a formula for nominal moment that you will use to calculate that MN. The trick is that you have to figure out which category, which mechanism of failure that your beam is going to be controlled by. In category 1, we call this the plastic moment. This category occurs when your beam's unbraced length is less than or equal to L sub P. L sub P is a dividing line. It's a value of unbraced length that divides category 1 from category 2. If you are in category 1, the nominal moment capacity is what we call the plastic moment capacity. And its formula is the simplest of all formulas, and it's shown there on the screen as Zx times Fy. The second category is called inelastic lateral torsional buckling. And this occurs when your unbraced length is between the dividing line called L sub P and the dividing line called L sub R. So again, L sub P and L sub R are limiting lengths, and if your unbraced length is between those, you are controlled by category 2 behavior. And as you see there on the screen, there's a formula for nominal moment capacity when you are in this inelastic lateral torsional buckling mode. It's a little bit longer of a formula, a little bit more complex. You take it a piece at a time, but there it is. The third one is elastic lateral torsional buckling. This occurs again in a lateral buckling mechanism, but it's elastic. It happens at low stresses. It occurs because your unbraced length is very long. Now your unbraced length is greater than L sub R. It doesn't happen all that much. It could, and I doubt we've seen it happen all that often in our problems so far. So which mode controls? Again, it is based on your unbraced length measured against the two dividing lines L sub P and L sub R. We've talked about this before. The only thing I'd again mention to you is the L sub R formula that you see there is a conservative formula. If you have the AISC steel manual at your disposal, you could look up in Chapter F of the specifications, and you'd see a much longer formula, which is more exact, more precise. There's also other parts of the AISC manual that you can look up. Values for LP and LR, they're right there for different a certain type of steel. But if you don't have that, you can use this conservative equation. It's not going to give you the exact same value as the longer equation would, but it's good enough for what we're doing. We've seen this, PowerPoint showing you how MN changes depending upon what category you're in. You're in plastic moment category is category 1. If your unbraced length gets longer, the nominal moment capacity actually changes. It actually decreases as you approach the LR dividing line. And as you go over the LR dividing line, your nominal moment capacity even decreases further. So how are we going to use this information to design steel beams? Well, there's several methods that you could use to design. If you don't have the steel manual in front of you or at your disposal, I think you're really left with trial and error. Now, trial and error could be just, hey, I'm going to select a beam and see if it works. That would be a pretty crude method. It would be nice if we'd be able to use some of the things that we've learned up to this point. And so basically what I'd like to propose to you right now is let's think about what we've seen so far. So far we've done several examples, and you've probably done multiple homework problems. And I'd say in just about all those homework problems you were either seeing your steel beam controlled by category 1 or category 2 type of behavior. It's rare that category 3 crops up. But let's for a moment say, let's assume that we're going to be controlled by category 1. This is a pure assumption. There's nothing that holds us to it. But if we assume we're category 1, the equation for design moment capacity is pretty simple. And we could go ahead and directly solve for the plastic section modulus ZX. So let's go ahead and let's do that. Whether we're using ASD or whether we're using LRFD, let's go ahead and solve for ZX. If we can solve for ZX, we can go right to a property table and we can pick out a section that has that ZX or a greater ZX than that. So we've got a section picked out. Now this is based on the assumption that it's category number 1, that it's controlled by plastic section, the plastic moment. So that's just an assumption at this point. How can we quickly go ahead and see if this is in fact a good assumption or not? There's a couple ways we can do it. I mean, one way would be to calculate LCP and see if our unbrace is less than or equal to it. The other thing that you can do, since this might involve several trials, is you can actually go ahead and rearrange the LCP formula to solve for an RY value. And you can do this by setting your unbraced length equal to this LP formula and solving for RY. What this RY value then is a minimum RY value to achieve the category 1 type of behavior, to fall in category 1. So what you could do is if you solved for ZX and you chose some member, let's say it was a W12 by 50 based on this step, you could go ahead and do this step and solve for RY minimum, and you could look at the W12 by 50's RY value, and if it is over this calculated RY minimum value, you would be in category 1. So the RY minimum that I'm talking about on this page is a value to put you, a minimum value to put you, if you're over that, into category 1. It assures that you're in category 1. So, and if you fall short, then that section would be in category 2, and you'd have to go ahead and proceed sort of on that trial in a long-handed fashion. But anyway, that's a little technique that we can use for trial and error method for beam design that might help you out.